cube roots of unity. What do you mean by cube roots of unity? Now, if you cube roots of 1, unity means 1. So cube roots of 1. So suppose I want to find out the cube root of 1. So I say let x is equal to cube root of 1. I say let x is equal to cube root of 1. So I get x cube is equal to 1. That means I get x cube minus 1 is equal to 0. That means a cube minus b cube must be equal to 0. That means x minus 1 into x square plus x plus 1 is equal to 0 from a cube minus b cube formula. That means we are getting either x is equal to 1 or x square plus x plus 1 is equal to 0. Now this is a quadratic equation, right? This will give us two more roots of this equation. Since this is a cubic equation, it will have three roots. This x square plus x plus 1 will give me two more roots. What are the roots? By Sridhar Acharya formula, you will find that these two roots will be minus 1 plus or minus I root 3 by 2. Now, this is something that is very special. You have to remember this. Okay, that this is minus 1 plus or minus root 3 is the cube root of unity. Now, if I call omega is equal to minus 1 plus I root 3 by 2, then it can very easily be shown that omega square will be the other one, the other root. This is a very special property, that if one root is omega, the other root is omega square. Okay, this is one property. The next property is that 1 plus omega square must always be equal to 0. Always, you can check. 1 plus omega square is equal to 0. The third property is that if you cube omega, you will get omega cube is equal to 1. And the fourth property is that omega is the reciprocal of omega square and omega square is the reciprocal of omega. These four are very, very special properties. Omega is called the cube root of unity, called the complex cube root of unity. Called the complex cube root of unity. Okay. So we are going to use these properties in order to solve some of the problems. So let us see what the problems are here. Look at this very simple problem here. 64 3. 64, yes, 64 3. Given that 1 omega square are cube roots of unity, so 1 omega square are cube roots of unity. Okay, show that you need to show that left hand side is equal to 32. 1, and what is the left hand side? 1 minus omega plus omega square to the power of 5 plus 1 plus omega minus omega square to the power of 5. You need to show that this is equal to 32. Now if you see this property here that I just wrote, 1 plus omega square is equal to 0. From this, what can you say? You can say 1 plus omega is equal to minus omega square, right? Or you can also say 1 plus omega square is equal to minus omega, right? You can say, so you're going to use this. So what you do here is you write this as 1 plus omega square minus omega to the power of 5 plus 1 plus omega minus omega square. Power of 5. Now what is 1 plus omega square? As I showed above, 1 plus omega square is minus omega. Minus omega to the power of 5. And 1 plus omega is minus omega square. Minus omega square minus omega square to the power of 5. So you get what? Minus 2 omega to the power of 5 plus minus 2 omega square to the power of 5. So this is what? Minus 32 omega to the power of 5 minus 32 omega to the power of 10. So this is minus 32. Omega to the power of 5 can be written as omega cube into omega minus 32 omega to the power of 10 can be written as omega cube into omega cube into omega cube into omega, right? Why did we write it in this way? Because we know that omega cube is equal to 1 from this property here. We know that omega cube is equal to 1. We are going to use this property. So if omega cube is 1, this becomes minus 32 omega, and minus this is 1, this is 1, this is 1. So you're getting minus 32 omega. Okay, minus 32 omega. So therefore, this becomes this minus 32 omega to the power of 5 can be written as omega cube into omega square. So this becomes omega square. Now what you can do is you can take minus 32 common. You get omega plus omega square. So you get, now see that 1 plus omega square is equal to 0. What does it mean? That omega plus omega square is minus 1. So you get minus 32 into minus 1, which is equal to 32, which is equal to your right hand side. So you see what properties have we used here in order to solve this sum? We used this 1 plus omega square is equal to 0, this property. We use 1 plus omega is equal to omega square. We use 1 plus omega square is equal to omega. Not only that, we also used omega plus omega square is equal to minus 1. This property we used. We also used omega cube is equal to 1. Okay. So that is one application of uh, cube roots of unity. Let us see another application. Anyway, so let's continue with 64.1. You have, if alpha and beta are the cube roots of unity, prove that. Okay, so left hand side is 1 plus alpha. So remember that alpha and beta are the cube roots of unity. Okay. So what are the cube roots of unity? What are the complex cube roots of unity? Omega and omega square. They are the cube roots of unity. So what you do here is you substitute alpha is equal to omega and you substitute beta is equal to omega square. Okay, because omega and omega square are the cube roots of unity. Therefore, what does the left hand side become? 1 plus omega 1 plus omega square 1 plus omega alpha is omega, so this becomes omega square, and this becomes 1 plus beta is omega square square. Now what happens? 1 plus omega is minus omega square according to the property. 1 plus omega square is minus omega. 1 plus omega is again minus omega, and this is 1 plus omega to the power of 4, right? So this becomes what? Minus omega There's a minus sign here, there's a minus sign here, there's a minus sign here. Three minus signs. So we retain the minus sign. And omega, what is the power of omega? 2 plus 1 plus 1, which is 4 into, and what you do here is 1 plus omega to the power of 4. You write this as omega cube into omega. Why? Because omega cube is 1. And now omega to the power of 4 also, you write this as omega cube into omega. 1 plus omega cube into omega. Now you substitute omega cube is equal to 1. So minus omega into 1 plus omega. Now what is 1 plus omega again? 1 plus omega is minus omega square according to our properties. So which is omega cube, which is equal to 1, which is equal to your right hand side. So very, very simple applications of cube roots of unity. Similarly, you have 64-4 also. Okay, 64-4. You have given omega square. Oh, 64-4 I have already done, no? No, I have not done. Okay. Given 1 omega square cube roots of unity, prove that. So we start from the left hand side. X plus y whole square plus x omega plus y omega square plus x omega square plus y omega square. Okay, so what should I do here? Expand first. This becomes x square plus 2xy plus y square, a plus b whole square formula, plus again this is your a plus b whole square formula, x square omega square plus y square omega to the power of 4 plus 2xy omega into omega square will give you omega cube plus x square omega to the power of 4 plus y square omega square plus 2xy omega cube. Okay, now we use the property of that omega cube is equal to 1. So you write this as x square plus 2xy plus y square plus x square omega square plus, now y square omega to the power of 4 can be written as omega cube into omega plus 2xy omega cube is simply 2xy because omega cube is equal to 1 plus x square omega to the power of 4 can be written as x square omega cube omega plus y square omega square plus 2xy. Okay, so now what happens? Simplify. X square plus 2xy plus y square. X square omega square, nothing can be done with this. You write simply x square plus omega square plus y square omega cube is 1. So this simply becomes y square omega plus 2xy plus x square omega cube is again 1. So this becomes x square omega plus y square omega square plus 2xy. Okay. Now what happens? How many 2xy's can you see? You can see 2xy. Here is 3 is in fact. This is 2xy. This is 2xy. This is 2xy. They combine to become 6xy. Right? Now x square, what can you see? Here you have an x square. Here you have an x square. And here you have an x square. So what happens? If you take the x squares together, what are you getting? 1 plus omega square. Okay. And what about your y squares? Here you have a y square. Here you have a y square omega. Here you have a y square omega square. So if you take the y squares together, become 1 plus omega square. Now what is 1 plus omega square? According to the properties, it is 0, right? So this becomes simply 6xy, which is equal to RHS. That's it. Okay, so this is your uh, applications of cube roots of unity. Okay. Now, what I would like to start today is a little bit of permutations. This complex number is over. Okay.
Yes, sir.
Permutation actually means permutation. Permutation actually means arrangement. This word is very synonymous uh, with permutation. Okay. Whenever I say permutation, it means arrangement. When I say combination,
Selection.
it means selection. Now, how does permutation work? First of all, suppose you three students are there. Okay. Uh, let me denote you by D. Okay, so you are D, Tanisha is T, and Sumit is S. Three students. And you have two chairs. Okay, you have two chairs. The question here is, in how many ways can you be arranged three students? In how many ways can these three students, D, T, and S, in how many ways can they be arranged in these two chairs? Say I call this chair 1, call this chair 2. How can you be arranged? See, first of all, I can make you sit in this chair, or Tanisha. Let us say let us consider chair 1 first. This chair. Okay. What I can do is I can make you sit in this chair, or I can make Tanisha sit in this chair, or I can make Sumit sit in this chair. Right? So in how many ways can I make you sit in this
Three.
chair? Three ways. I can either make D sit, or T sit, or S sit. So I can make one student sit in one chair in three ways.
Yes, sir.
One student in one chair in three ways. Right?
Yes, sir.
Next, consider the next chair, chair number 2. This chair. Right? Now, once I have made one student sit here, any one of you, okay, any one of you sit. Suppose Sumit sits here. Okay, so suppose Sumit sits. So one chair is empty. How many students left? Only D and T are
Two.
left. Right? So now D and T can sit in the blue chair in how many ways? Either Tanisha can sit or Devanjan can sit. So in how many ways can you sit?
Yes, two ways.
So one student in one chair in two ways. So in how many ways can all of you sit in the two chairs? And in how many ways can three students sit in two chairs?
5 ways.
Why five ways? First three students are sitting, and then to first two ways. First three ways, right?
Yes,
And
sir.
then remember, and is the keyword here. And means multiplication, or means addition. Remember this. So that means three ways and two ways,
2 ways.
right? So therefore, and means multiplication. Then therefore, what is the total number of ways in which you can sit? 3 into 2, which is
6 ways.
6 ways. This we call a permutation, an arrangement of three students taken two at a time. Three students. This is the arrangement of three students taken two at a time. And this we call 3p2. Understood? This was a very, very simple example. Is this clear?
Yes, sir.
Now, suppose if there were four students and three chairs, in how many ways will you make them sit? In how many ways?
4p3.
4p3. Exactly. So that is how permutation works. Next we come to what is the value of 4p3. Okay, suppose I take 15p5, then how will you calculate this value? 15 things taken 5 at a time. How do you calculate this value? See, the formula for the formal relation in order to calculate is NPR, permutation of n things taken r at a time. NPR, the formula is factorial n by factorial n minus r. I'm coming to the factorial notation after this. Okay. Now, what do you mean by factorial? Sometimes this is also written as in this way, factorial n by factorial n minus r. Okay. This is what our formula for NPR is, factorial n by factorial n minus r. Now, what do you mean by factorial of a number? Suppose I want to calculate 3 factorial. 3 factorial means 3 into 2 into 1. Understood? 5 factorial. 5 factorial means
5 into 4
5
into
into
3
4
into
into
2
3
into
into
1.
2 into 1. Suppose 10 factorial. It is 10 into 9 into 8 and you carry on until 3 into 2 into 1. This is what we define the factorial of a number as. Okay. So therefore, if I want to, let us take an example here and see, suppose if I want to calculate um, 6p4, how will I calculate this? This is factorial 6 by 6 minus 4 factorial, which is factorial 6 by factorial 2. 6 minus 4 is 2. Now, what is
Yes.
factorial 6? 6 into 5 into 4 into 3 into 2 into 1.
120,
And factorial 2 is simply 2 into 1.
360,
So this cancels. Okay, so you simply get 6 into 5 into 4 into 3. Um,
120 into 3,
this is the value.
360.
Okay, whatever you get after multiplication. But this is the value of 6p4. Now see, sometimes always using the formula to calculate NPR becomes sometimes a little difficult because you have a factorial in the numerator, you have a factorial in the denominator. Okay, I'll give you a shortcut to calculate NPR. Now see here, what do you see? 6p4. What have I got here? 6 into 5 into 4 into
Mm,
3. Without using this
yes, sir.
formula, you can directly write this. How will you write? See, 6p4 is there. See, and here you have 4, right? So how many terms are there? 1,
4.
2, 3, and 4. Right? And you start from
Yes, sir.
6 and you keep decreasing by 1. So similarly, if I have to write, say, 10p5, how will I calculate this? 10 and
10
then
people,
9 and then 8 and
8,
then 7 and then
7,
6
6.
and then stop. Because now I've
Yes, sir.
already got here the 5 and here I have 5 terms. Understood? So
Is
instead
that a
of,
formula?
no, this is a shortcut. You're actually getting the shortcut from the formula only. Understood? But
But we can
this,
apply that. No.
yes, you can apply it directly, no problem. Always using the formula will be difficult. Actually, from the formula, what do you get? From the formula, you'll get factorial 10 by 10 minus 5 factorial, which is factorial 10 by factorial 5. So if you calculate, it will come to
Mm,
this only. Suppose if I
yes,
want to
sir.
calculate 9p 9p8, 9
Mm.
into 8 into 7 into 6 into 5 into 4 into 3 into
We can
2.
even stop at 8 factorial, 9 into 8 factorial, and down
Yes, you can
and down.
also. I'm coming to that. Okay, now what is a very again a very important observation here is that suppose it's 10p5. If I want to write, then I'm writing this as 10 into 9 into 8 into 7 into 6. Very important observation here is that, yes, you can also write it that way. Um, but the important observation here is that for the factorial of a number, okay, not for 10p5, no, not for NPR. Okay, NPR stops here only. Okay, I'll give you a very interesting property of factorial. But what you learn from here is that if you want to calculate 9p8, you have to list till You start from 9 and you must have 8 terms, right? You have
Yes,
8
sir.
terms. Suppose you want to calculate 5p2. How will you calculate? 5 into 4 simply, right? Because here you have a 2,
Yes, sir.
so you'll get only 2 terms. Okay, that is how you calculate NPR. But however, the formula for NPR remains, and you will have to remember this formula if anything direct application of this formula comes. Okay, normally we use the shortcut. Normally we use the shortcut for for if when we are doing applied problems on permutations. Okay, so for your one and very interesting observation with factorial of a number is, that 10 factorial is 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. So one very important observation is that 10 factorial can also be written as 10 into 9 factorial, right? Similarly, 11 factorial can be written as 11 into
10 factorial.
10 factorial. Or you can also write this as, you can also write this as 10 into 9 into 8 factorial, which can also be written as 10 into 9 into 8 into 7 factorial, right? Which can also
Yes,
be written as 10 into 9 into 8 into 7 into 6 factorial. Okay, and so on. Similarly, 11 into 10 factorial, you can write this as 11 into 10 into 9 factorial, which can also be written as 11 into 10 into 9 into 8 factorial, which is 11 into 10 into 9 into 8 into 7 factorial, and so on. Clear? So this is one
yes, sir.
very interesting property of factorial. Remember this. Therefore, in general, what can we write? Factorial n. What can we write? N into n minus 1 into n minus 2
Mm.
into n minus 3 factorial, right?
Yes, sir.
In fact, you can write. Let me write just two more steps here. N into n minus 1 factorial. You can write. You can write this as n into n minus 1 into n minus 2 factorial. You can write this as n into n minus 1 into n minus 2 into n minus 3 factorial, and so on. You can continue this way. It can be shown, if you continue this way, it can very easily be shown that factorial n is n into n minus 1. It can not this, not factorial of a number, but in fact, it can very easily be shown that NPR is equal to n into n minus 1 into n minus 2 up till n minus r minus 1. Okay, so this is what you need to remember. So please remember the properties of factorial. Please remember the formula for NPR, and please remember the shortcut, how to use NPR, and the concept
Sir,
of
I couldn't
NPR also.
understand the last one.
Which one? The last one.
Last one.
If see, NPR can also be written as n into n minus 1 into n minus 1 into n minus r factorial. Actually, what happens? Let me just derive this for you. What happens is that, this is not NP5, this is NPR. Was this the confusion?
No, no, sir. You can derive that.
Factorial n by factorial n minus r. Okay, this is what. So now this you can write using the above property, you can write this as n into n minus 1 into n minus 2
Yes, sir.
and continue till n minus r, um, n minus, you can continue this till n minus n minus r minus 1, okay, into n minus r, okay, factorial. You can write it this way, divided by n minus r factorial. Therefore, these two are going to cancel, n minus r factorial. What are you left with? N minus 1, n minus 2, up till n minus r minus 1. Now you might say we are using n and r, that is why you're getting confused. If you remember this only,
Yes, sir.
if you remember this only, where is it going? This step, it is sufficient. Okay, this is actually this term that we are writing, these four. This is actually n into n minus 1 into n minus 2 up till n minus r minus 1. Understood? So
Mm.
remember this relation. If you remember, it is okay. This one, the last one, if you remember, it is okay. If you don't remember, it is also fine. But remember this property, very important property, all these of factorial of a number. Expression for NPR. What is the meaning of NPR? Arrangement of n things taken r at a time. Okay. And how to calculate NPR in shortcut. That is what you need to remember. Okay. So I stop here for today.